We will derive the unit circle in this video, and it serves for the basis of the study of trigonometry. Let's begin by looking at a circle that is centered at the origin 0, 0 with radius 1. And look at the coordinates where the circle intersects the positive x-axis. The coordinates of that location would be 1, 0. The coordinates for the negative x-axis would be negative 1, 0. If we look at the positive y, we would have 0, 1, and negative y would be 0, negative 1. That confirms that the circle is oriented with the origin as its center and it has radius 1. Next, we will turn to the degree measures for the angles, and we're going to work our way around the circle. First, we need to understand what standard position is. Standard position means you start from the positive x-axis and you begin your rotation in the counterclockwise direction. This is helpful for how we form our angles going around the circle. With that in mind, before any rotation takes place, we will start with 0 degrees along the positive x-axis and then work our way around. I like to begin with starting with 90 degrees. 90 degrees in the counterclockwise direction would be in the positive y-axis. And take that 90 degrees and count another 90 degrees. We would land on 180 degrees. That would be half of a circle. 180 degrees plus another 90 makes 270. 270 and 90 more makes 360. Now 360 degrees means we've made one complete cycle around the circle, and 360 degrees is coterminal with 0 degrees. Next, let's take a look at quadrant 1. We have this 90-degree angle here, and if we take 90 degrees and divide it by 2, we would form 45 degrees perfectly in the middle. So let's label 45 degrees right here, and we're going to count our way around the circle using multiples of 45. 45 degrees plus another 45 makes 90. 90, and if we count 45 degrees more, we would have 135 degrees. Now we're in the middle of quadrant 2. 135 plus 45 more makes 180. 180 plus another 45 makes 225. 225 plus 45 more is 270. 270 plus 45 is 315. And it's good to confirm that 315 plus 45 more makes 360, one complete circle around. Let's look at quadrant 1 one more time. Here's our 90 degrees. And if we divide 90 into 3 equal angles, we would have 30 degrees. 90 divided by 3 is 30 degrees. So that angle there forms 30 degrees. Here we have our 30, and we're going to count multiples of 30. 30 plus another 30 makes 60. 60 and 30 make 90. Then we'll have again 120. 120 plus 30 is 150. And 30 degrees more makes 180. There's our half a circle. 180 plus 30 more, 210. And then I'll count our way around. 240 plus 30 makes 270. 30 more is 300. 300 plus 30, 330. And 30 more makes 360. Now we've gone all the way around one complete circle with our degree measure. Next, we will talk about radians, which are important here. Radian will not have that degree symbol. The units will simply be radian, and we're going to begin in standard position. 0 represents 0 radian right here, which is equivalent to 0 degrees. Next, it's helpful to know conversions. If you've discussed the conversion before, that 180 degrees converts to pi. That's helpful to know. Or you could know one complete circle around makes 2 pi radian. And then I like to take a look at pi here, which is equivalent to half of a circle. And we're going to divide that pi radian into 2. That's a half of a pi. So to label that on the circle, 90 degrees would be equivalent to pi over 2. So I'm going to label that as pi over 2 radian, and then count multiples of pi over 2. For example, 90 degrees is 1 pi over 2. 180 degrees is 2 pi over 2, which reduces to pi. And then the next unit would be 270 degrees, which is 3 pi over 2. And then go another 90 degrees, which would make 4 pi over 2. which is equivalent to 2 pi radian. So we've made it all the way around a circle with multiples of pi over 2. Next, let's take a look at pi over 2 radian, and we're going to divide that unit into 2. Pi over 2 divided by 2 would make pi over 4. So pi over 4 radian is equivalent to 45 degrees. Let's label 45 degrees being equivalent to pi over 4, and let's count those multiples of pi over 4 in a similar way that we counted multiples of 45 degrees. We have 1 pi over 4, 2 pi over 4 reduces to pi over 2. Next we have 3 pi over 4, and then 4 pi over 4 is equivalent to pi, and we have 5 pi over 4, the next multiple of pi over 4. 6 pi over 4 reduces to 3 pi over 2. And then the next one is 7 pi over 4. And lastly, we have 8 pi over 4, which is equivalent to 2 pi. Hence, we've made it around using multiples of pi over 4. And then another way to see this here is to discuss multiples of pi over 6. Let's see where they come from. This one, you want to be really careful. See that as pi from the first two quadrants, and it's divided into 6 equal pieces. 1, 2, 3, 4, 5, 6. So that forms pi over 6 radian. So 30 degrees is equivalent to pi over 6 radian. You could also check your conversions that 30 degrees converts to pi over 6. So what we will do here is count multiples of pi over 6. There's 1 pi over 6 at 30 degrees, 2 pi over 6 at 60 degrees, but I'm going to reduce 2 pi over 6 as pi over 3. Then the next one is 3 pi over 6, reducing to pi over 2. 4 pi over 6 reduces to 2 pi over 3. The next one is 5 pi over 6. And lastly, 6 pi over 6 lands on the pi. There's our half of a circle. Keep counting multiples of pi over 6. We're at 6 pi over 6. Next one is 7 pi over 6. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. And then we have 11 pi over 6 before we reach 12 pi over 6. 12 pi over 6 is your 2 pi. Hence, we've made it all the way around the circle with multiples of pi over 6. It's also helpful to confirm these angles right here. If we're looking at our pi, and then if you look at the dashed lines on this unit circle form pi thirds. So if we have the half a circle forming pi, that's cut into 3 equal pieces, 1 pi over 3, 2 pi over 3, and then 3 pi over 3, 4 pi over 3, 5 pi over 3, and then 6 pi over 3, which becomes 2 pi. And that's how I recommend counting the patterns for the multiples of the radian. And next, we need a little bit more organization for where these coordinates come from. And it comes from the study of the special right triangles. This part here is really important to know your 30, 60, 90 degree triangles and your 45, 45, 90 degree triangles. I'm going to talk about them very briefly here. Let's take a look at quadrant 1 more time and consider this coordinate here. Those are the coordinates we're looking for, x, y. I'm going to draw a segment down to the origin and then connect that point in quadrant 1 down to the x-axis. And I'm forming a right triangle right here. And the smallest angle that forms is 30 degrees. So this angle right here from standard position forms a 30 degree angle. And then we have 90, so that means the 60 degrees is up top. I know we have a lot going on here, but look only at the purple for now. Let's recall that this is the unit circle. The unit circle means the radius is 1, so that means the hypotenuse of this triangle is 1. And then if you understand your 30, 60, 90 degree triangles well, that means the small side of that triangle will be half the size of the hypotenuse. So I'm going to take that 1 divided by 2 and form 1/2. Then the medium side of that triangle would be rad 3 over 2. You take that small side 1/2, multiply it by rad 3, and get rad 3 over 2. Confirm that those sides of the triangle make sense to you. That is in the 30, 60, 90 degree triangle ratios. And the coordinates that we form here on this unit circle will be the x-coordinate. The x-coordinate is the segment along the x-axis, and that x-coordinate being rad 3 over 2. We go to the right, rad 3 over 2. And then if we go up, the y-axis would go up by 1 over 2. Confirm that those coordinates make sense, x and y being rad 3 over 2 and 1 over 2 respectively. Okay, so then if we take a look at the 60 degree measure right here, the 60 degree angle would form a very similar triangle where the 60 degrees would be in standard position. That means the medium side would be the y segment. I'm going to label the y-axis, or the y-coordinate, that is, rad 3 over 2. Then the x-axis would be the smaller segment because the 30 degrees would be up top. That means the x-axis would be the 1 over 2. Then we can use symmetry. If you compare what's in the quadrant 1 to quadrant 2, the first coordinates that we did, rad 3 over 2, comma 1 over 2, if I go immediate to the left, if the x-axis becomes negative to the left, we would have negative rad 3 over 2, comma positive 1 over 2, because the y-coordinates are positive in quadrant 2. Next, looking at that last triangle that we drew with the yellow highlighter, if it was positive x being 1 over 2, negative x would be negative 1 over 2, going to the left the same amount as we went to the right. And then if the y-axis is the same, it would be rad 3 over 2. Okay, next, if we take a look at this triangle here, I'm going to mark this triangle here in orange. We have a 45, 45, 90 triangle. And remember that the hypotenuse is 1. That would make rad 2 over 2 as each of the two bases. It is a 45, 45, 90 triangle, so each base segment would be exactly the same. And they would be in that ratio of rad 2 over 2, rad 2 over 2, where the hypotenuse is 1. You can confirm by Pythagorean theorem that those segments are the same. Then, if it was positive x rad 2 over 2 to go immediate to the left, negative x would be negative rad 2 over 2, and the y-coordinate would be the same. Now I'm going to count my way around the unit circle here. Let me use the 45, 45, multiples of 45 going all the way around. I'm going to find these two coordinates next. In quadrant 3, you're going to have negative x coordinates and negative y coordinates. And then notice the segments are all rad 2 over 2. And for the 45, 45, 90 triangle formed in quadrant 4, which would be this triangle here, it would go rad 2 over 2 to the right in the x direction, and the y coordinate would be negative rad 2 over 2 because we're going down by that same amount. Let's go back to the original 30, 60, 90 triangles we did, and we can use a lot of symmetry here. If we have rad 3 over 2 as the x coordinate, to go to the left, we would have our negative rad 3 over 2. And then to go to the right, we would have positive rad 3 over 2. Let me go back to quadrant 3. And in both of these, in quadrant 3 and 4, we're going down. And we're going down the small segment. We're going to go down 1 over 2 and down 1 over 2. So I'm going to represent each y-coordinate as negative. And then finding the symmetry to the multiples of the 30 degree angle. Let's see here. The 30 degree angle, let me mark that back in the purple here. We would have, the yellow. Let me match that with the yellow highlighter. This triangle here in quadrant 2, this triangle here in quadrant 3. So let me compare quadrant 2 to quadrant 3. Both of those go left, the small segment of the triangle. To the left, we went 1/2, so I will mark that as negative 1/2. And then I'm going to go down the same amount that I've gone up. If in quadrant 2 I went up rad 3 over 2, quadrant 3 we will go down rad 3 over 2 and mark that by negative rad 3 over 2. And then last quadrant here, quadrant 4, we have that Symmetry going on with that 30, 60, 90 triangle. Quadrant 1 went to the right 1 over 2. So quadrant 4 will also go to the right 1 over 2. And then I'm going to go down the medium side, which is negative red 3 over 2. So take a look at that completed unit circle. Look at all of the symmetry. Notice when the x-coordinates are positive, when we went to the right. When the y-coordinates are positive, whenever the y-coordinates went up. And then make your way around the circle. Know all of those patterns between the degree measures from 0 to 360 in standard position, as well as the radian whenever we have pi's, the multiples of pi, and then the subdivisions of pi as well.